So in this video, I would like to explain how it is possible to design numerical simulations at the super resolution. And this is to estimate time constant statistics or any statistics of interest from data inside an image. And so this is, again, work that has been done a couple of years ago. Our algorithms are available at our website bionumetrics.org. So first of all, let me explain the idea and the concept. Suppose you are able to obtain trajectories. Here they are in this nanodomain label 1, 2, and 3. Here we have 4. It's a magnification where you show that we can see here trajectory. Each color corresponds to a single trajectory. So if you look at the resolution of this compared to, for example, the resolution of the microscope, you realize that these trajectories that have been acquired at the super resolution are much well resolved compared, for example, to a confocal image. So yet we can estimate from this trajectory, and we have developed technique in the past. You can look at the density, so you fix a grid, and on the grid you look at the number of points that you obtain, and you color each bin according to the density. So this is done here. So this is an example where you see discretization in this very coarse grid. And you can get information, for example, such as the diffusion coefficient estimated at the grid. So the first thing that is important to note is that if the diffusion coefficient is different for different grid, we have a discontinuity in the diffusion coefficient. And this is an artifact coming from the discretization methods. Diffusion constant should be constant, or should be smooth at least. So something is needed here to compensate this artifact obtained by this procedure of estimation. So what we're interested in this video is to understand, to do some image analysis, and specifically I would like to introduce a spatial filter to be able to generate the trajectory as if they were obtained from the experiments. So the question is how to generate trajectory in the image, for example, of a dendrite, a neuron, an axon, obtained usually by a confocal image of microscopy, while the trajectory where we get the statistics have been acquired at a super resolution. So for example, we can get a resolution of less than 200 nanometer, like 10, 20, 40 nanometer for the trajectory, while the image resolution is 160. So we would like to keep the information about this very accurate resolution and still use this in an image that was not super resolved but contains the information about structure. And so for this we need to discretize the image into a pixel. And by doing this we obtain piecewise constant value for drift and diffusion coefficient at each point. So this procedure, the discretization procedure of the space here in small square, so this generates this local discontinuity and create this can create artificially non-connected region. So let me show you an example. This is here the confocal image where you see a structure like a dendritic spine. Now you can discretize and obtain the information from the trajectory to extract what we have seen before, the diffusion coefficient, so that each box here we have estimated the diffusion coefficient, and this is shown here in the bar scale. So this is one, we get the this information from the trajectory. We get this for the diffusion, and we can also get this for the drift. That is, at each point we can calculate as can be seen here. We can calculate a little. So I'm doing here. We can obtain a vector field, which is going to be our drift. So this allows us to basically recover the two element for stochastic equation, which is x dot equals a of x plus sigma of s, the diffusion tensor w dot, which is the Brownian motion. And of course, if I know a at each point and sigma, I can generate any trajectory I want by just simply simulated this stochastic equation. But for this, I need to have the information. So if I have a grid, I'll go back to this resolution. If I have a grid, then I need to be able to have this at each element of the grid. Suppose I have this information here, but not at the center. Then what shall we do? We can, for example, interpolate the information coming from here, here, and here, I mean from the neighbors. But if something is missing here, we are still in difficulty to understand which value we'll have to give here. And so this is what I would like to explain, how we develop the procedure by introducing here a filter. And after we filter, how we actually are going to deal with a situation where we have missing information. And the goal, once we have resolved this question, would be to generate, as we see in this part here. So here we generated a trajectory starting at one point, and we're interested in how this trajectory, for example, evolved. I'm doing it by hand in this structure. So we use now the confocal information, although it is not as precise, but it still gives us the shape of the structure to see when, for example, a trajectory arrives to a region of interest, as we've shown here. So now let me describe the notion of spatial filter. This can be extended, of course. So the first thing is that we can suppress squares surrounded by some that are not covered by experimental trajectories. For example, first of all, we can look at the square here that contains less than 15 points. If we have less than 15 points, we are going to eliminate, we are going to remove them. And so, so if we have here our image, we look at where we have this, this square, and in the first step, if they are less than 15, we eliminate. For example, this one has less than 15, so it is gone. The second step here is important because it is there to remove isolated square. So this is going from B to C. So for example, this square is isolated, so it's going to be removed. And finally, so this is a filter which we call filter 2 to suppress this isolated square where they are not surrounded by at least 4 neighbors. And the third one is a smoothing filter. And so this is shown here going from here to here, where we apply a low-pass filter. First of all, we increase, as you see here, we increase, we added locally a sort of completion by some classical algorithm to locally expand the region, and which is correspond here to this procedure. So this procedure is summarized here, where we have added the surrounding grid. And then we are ready here to obtain simulation by using this stochastic equation. So each component is piecewise constant for each. In each of these square, we have the drift B and the diffusion tensor. So again, this has been summarized in our paper with Nathanael Hoze in Biophysical Journal, published in 2014. So you can go to, so this is Hoze and myself, and this has been published in 2014 Biophysical Journal. And of course, now the question is, what happened when a particle arrived to the boundary of a domain? So we use here the classical law of reflection, which I have described in a previous YouTube video about reflecting the domain. So you reflect basically the trajectory inside the square. It can happen that it has to go, I mean, the reflection could be in the other in another part of the grid, and this we have to be careful. First of all, this grid, I mean, this bin here should be acceptable in the simulation. Otherwise, you can reflect it again, so it stays inside the bin it started with. We provided also a sort of time step. What should be the time step delta t of our simulation? This is always a tricky choice. For example, this is we gave here a sort of criteria that delta t should be small enough such that the mean square displacement should be less. I mean, 4 or 5 times the mean square displacement should be less than the resolution R. That, for example, could be the size R is here, the size of the grid. And once you have this, so that means that you don't want to make too big jumps when you're in the box. You know, this would not be acceptable. This should be okay. So this is to say that the mean square displacement should not be too big compared to R. And then you can, of course, adjust according to where you are, or take a delta t, which is the minimum delta t calculated over your entire grid. So you have your grid, and you look at all the pixels here, and for this you can estimate your delta t that depends on the drift and the diffusion tensor, and obtain, for example, a uniform delta t. So in summary, you can get this down by having this procedure. So we are going to release pretty soon an ImageJ plugin that will do this. So from your super resolution trajectory, you can obtain from the grid the diffusion coefficient and the drift. You can estimate any features of interest, such as potential well or drift, as we have discussed in the past. And you can do what we have described today, this description, where we use this, we discuss this spatial filtering to go from here to here. And now we can simulate using stochastic simulation the trajectory. And you can get long trajectories. This is the interest of the method. Now, I just would like to show you an example of something that can go wrong. So this is an example here where we didn't choose here correctly the step delta t. And so what happened is that the trajectory start to fill the entire square of the grid. And so this is incorrect, because then the time that you are going to get, let's say starting from here to go to here, is going to be enormous, which has nothing to do with the real time. So delta t also should not be too small. So it should be big enough. Should be large enough. So this is usually done empirically. So again, in the absence of filtering and this information about having a delta t not too small, you can get artificial confined in small square pixels. So now this is an example where everything works very nicely. So you start here at position, let's say position A, and we are interested in the first time where the particle arrive here in this in the boundary mark in this green region. So you see the trajectory here in blue, and so this is an example where we can generate long trajectory. The vector field here is the one described in this figure. So we had this this vector field, and we use each arrows here for the drift at each position. And so this is an example where, for example, you are interested in the time a receptor stays inside the dendritic spine. So what we do is you start implementing this procedure and end the simulation when the particle hits any point here of the circle. And from this you can obtain the statistics of the escape time. So you start here and you wait until the trajectory hit this point, and you get here, as described by the theory, a Poisson distribution. And you can repeat this, for example, by putting the drift to 0, just by turning a switch off the drift component. Or you can leave the drift. And from this you can see the effect of having a drift in these statistics, especially here when the drift is pushing the particle outside. So this is a way to get longer trajectory that you could not get from your super-resolve data, and thus to obtain statistics of interest, because the diffusion coefficient and the drift doesn't give you the time to stay inside such a structure. This has to be calculated from enough trajectory to get the statistics. And this is an example where the field is in the opposite direction. So instead of decreasing the time, it increases the time. But again, this the overall statistics is Poissonian. And I'll finish here this video about numerical simulation at the super resolution limit. And I think this is a great tool that can be used at each time you have data, super resolution data, and you are interested in estimating the statistics that is not contained in the data. Thus, you do the simulation.